Hello students, welcome to lecture 15 of the online course on Nanophotonics, Plasmonics and Metamaterials. In today's lecture, we will cover the emerging applications of photonic crystals. So here is the lecture outline. We will start with application of 1D photonic crystal. We will discuss Bragg grating briefly. Then we will move on to periodic dielectric waveguides. We will also look into some applications of 2D photonic crystals like photonic crystal slabs, photonic crystal fibers. We will also look into index guiding photonic crystal fibers and endlessly single mode fibers. So, let us look into the application of 1D photonic crystal. As I mentioned, we will study Bragg grating. So, Bragg grating is nothing but it is an set of uniformly spaced parallel partially refractive planar mirrors. So, you can see here. So, this is basically a Bragg grating. So, here we are showing that there are n identical mirrors. So, what happens in this grating when some incident light falls, some particular wavelength or frequency gets reflected, remaining gets transmitted. Now, such a structure has angular and frequency selectivity, and that is useful for many applications such as filter and then pulse compensation in optical fiber communication and so on. So, here we will generalize the definition of Bragg grating to include a set of n uniformly spaced identical multi-layer segments. So, the devices which are fabricated using this particular grating are distributed Bragg reflectors, DBRs, and fiber Bragg grating, which is FBGs in short, and they are often used in resonators and lasers. FBGs are also very popular for sensing application because depending on the surrounding media, the refractive index of the surrounding media can change, and that can change the wavelength of the reflected light, and that can be used as a sensing mechanism. Now, let us look into Bragg reflection in details. So, consider light reflected at a angle theta. So, here we are calculating the angle from the plane of the mirrors, and here are the m parallel reflecting planes which are separated by a distance of capital lambda. So, what happens? This light, little bit of this will get reflected and remaining will get transmitted. So, we assume that only small fraction of the light is basically reflected from each plane, and the amplitude of each of these reflected lights are assumed to be almost equal. Now, the reflected lights will have a phase difference because different light is actually traveling different distance, different ray here is traveling different distance. So, you can calculate the phase difference phi, small phi, as k times 2 capital lambda and sin theta. So, k sin theta is basically the component of the wave vector into this particular multi-layer structure. So, the phase difference will be k 2 capital lambda. Why capital 2 capital lambda? It has to travel this part twice, okay, and the angle at which the intensity of the reflected light is maximum, that is known as the Bragg angle. So, sin theta b is given as lambda over 2 capital lambda. What is capital lambda? The spacing between the mirrors. Small lambda is that particular wavelength of light. Now, such reflections are encountered when light is reflected from a multi-layer structure, and here I mention remember that theta is basically defined with respect to the parallel planes. Now, the reflection or reflectance of Bragg grating is basically determined under two assumptions. What are those? The first one is the mirrors are weakly reflective, so that the incident light is not depleted when it propagates. So, the reflection amplitude is basically very low. And second thing is that the secondary reflection, that means reflection of the reflected waves, those are considered negligible because the first reflected wave itself is weak. If you take this to approximation in mind, you can find out the reflectance of the n mirror grating which can be related to the reflectance R of the single mirror by this particular equation. So, Rn, n corresponds to the n mirror grating here, will be sin square n phi over sin square phi times R, and here phi denotes the phase between the successive phasors, whereas the phase is basically defined by 2 phi, and that is corresponding to a round phase or round trip phase. Okay, you can call it also round trip phase, that is why it is 2 phi. Now, this particular factor that you have seen here, sin square n phi over sin square phi, represents the intensity of the sum of the n phasors of unit amplitude and phase difference 2 phi. Okay. Now, the function can obtain a peak value which is n square when the break condition is basically satisfied. That means, you have to look for condition where 2 phi is equal to q times 2 pi. What is q? Q is like integer 0, 1, 2, 3 and so on. Now, the reflectance will also drop away from these values sharply. So, there will be a very sharp cutoff with a width that is inversely proportional to n. Okay. So, larger the n, sharper will be the cutoff. So, that is why larger the Bragg reflectance, you will get a higher order filter, you can say. Okay. And in this simplified model, you can actually see that the intensity of the total reflected wave is at most the factor of n square greater than the intensity of the reflected wave from the single mirror or single segment. Now, for a Bragg grating comprising partially reflective mirrors which are separated from each other by a distance of capital lambda, and we have seen that the round trip phase 2 small phi is basically 2k capital lambda cos theta, and theta is considered to be the angle of incidence. So, here you see this theta is not considered from here, it is basically this particular theta. Okay. So, in that case the equation will have cos theta. Okay. So, you can write 2k capital lambda cos theta can be taken as 2q pi. This is nothing but the phase, round trip phase should be equal to integral multiple of 2 pi. Okay. And from that, if you write 2 pi by k equals small lambda, you can actually get this in terms of small lambda and capital lambda. So, you can write cos theta equals q small lambda over 2 capital lambda. This can also be written as omega b over omega, that is the Bragg frequency over the normal frequency. Okay. Or you can this is the angular frequency, you can also write them in terms of linear frequency. Okay. Now, how we obtain this? Let us have a quick look. So, this is what you have seen, this is called the Bragg condition. Okay. This particular condition of theta on the incident angle is basically the Bragg condition. And here we have encountered two new terms, which is omega b, that is basically pi c over capital lambda, and nu b, okay, that is c over 2 lambda. So, what is the relationship between this and this? This is linear frequency and this is angular frequency. Okay. So, these are both Bragg frequencies. So, what you see here, that at normal incidence the peak reflectance occurs at frequencies that are basically integral multiple of the Bragg frequency, that is you have to look for frequencies which are nu equals, this is not nu b, this will be nu equals q nu b. Okay. So, this is just nu. Okay. And at frequencies where nu is less than nu b, means the Bragg condition is not getting satisfied at any angle, and for frequencies like which is less than this one nu b, okay, the Bragg condition is satisfied. Okay, I think there is also one typo here, it will be nu is here, nu b should be here. Okay, there is a typo again. So, it is like the frequency between nu b and 2 nu b, you can see that the Bragg condition is basically getting satisfied at one angle, and that angle is basically theta equals cos inverse of lambda over 2 capital lambda. Okay, or you can write it as cos inverse of nu b over nu. So you can actually see those calculations here. So here is a plot that shows the locus of frequencies. So this is the frequency and the angle at which Bragg condition is satisfied. Now if you take nu and nu b, the ratio to be 1.5. So if you draw this dotted line, you will see that you are getting theta equals 42.8 degree. So in that case, how do you get the Bragg angle? Bragg angle is basically this angle, that will be 90 minus this, which is 41.8 degree. So with that, we understand that how the Bragg grating works. Now if you take an example, specific example, that n equals 10, so you are considering only 10 identical mirrors, and we have also restricted the performance of the mirrors, like power reflectance modulus of small r square is taken as 0.5, and in that case, okay, we will see how the performance of this mirror looks like. Now dependence of capital phi, okay, on the intermirror phase delay small phi is this one, right? What is small phi? That is a phase delay n k naught lambda, that is like from one mirror to another, what is the phase delay. This is not the round trip phase delay, this is the intermirror phase delay. Okay. Now if you plot this, okay, you will see that within the shaded region, this capital phi is basically complex, and the imaginary part are actually shown here by dashed curves. So what is understood here is that, you know, this is also periodically repeating. Now if you try to plot reflectance R based on the previous formula that you have discussed as a function of frequency, okay, you can actually convert them into the Bragg frequency, which is nu b given by c over 2 capital lambda. Okay, you will see that you are getting clear stop band. Stop band means, you know, you are getting reflectance completely 1, okay, and then suddenly it drops, and then again it goes back. So at every nu b, integral multiple of nu b, okay, and at 0 you will get this stop band. Okay. So that's how you can actually use Bragg grating as a particular band stop filter, and you can actually make it reflect a particular wavelength. Now if you take specific example of creating a Bragg grating like this by alternating two different dielectric material, like N1 and N2. So here N1 is 1.5, N2 is 3.5, and D1 and D2 are taken to be equal, and you have 10 such segments. So low, high, low, high. So this kind of low high segments you have repeated 10 times, okay, and you have placed this entire grating. This is called dielectric Bragg grating. You have put this entire grating in a medium of refractive index N1, okay, and after you calculate, okay, you the reflectance versus frequency, you can see that, you know, the stop bands are basically centered at this particular wavelengths, okay, lambda b, nu b, 2 nu b, 3 nu b, and so on. Okay. So here you can find out that nu b is nothing but c over 2 capital lambda. What is capital lambda? That is basically the period. Here the period is marked. Clear? So this way you are able to get good frequency selective performance from Bragg reflectors. Now let us move on to the next topic, which is basically periodic dielectric waveguide. So periodic dielectric waveguide, which have only one dimensional periodic pattern or grating kind of thing, okay, along the propagation direction, but in this case they have finite thickness and width, okay, that is the only difference. So in the previous case we have considered all to have infinite in this direction, only in one direction we are bothered. So let us look into some of these examples. So many periodic waveguide structures are possible. So few are shown here. As you can see, this is basically one dimensional array of holes, okay, and these are all like that. So these are basically array of dielectric columns. So here index waveguiding is possible in the two transverse direction. So while the periodicity is along this x direction, in this case The index guiding is possible in z direction. So based on, because it will like high index material surrounded by low index air, so you will be able to guide modes along the length of this wire. Okay. So that is how index guiding can take place along y direction, or sorry, z direction, and in this case it is periodic along x, and the index guiding can take place along the other transverse direction, that is y direction. So it will turn out that regardless of the geometry, whatever is the geometry that you are seeing here, these structures, they exhibit a common phenomena. And what is that? They have a form of photonic band gap along their periodic direction. So along this direction where they are periodic, they have a photonic band gap, and they can confine light in other directions, like in this direction or in this direction, they are able to confine light by the principle of index guiding. We can also look for two dimensional periodic patterns, okay, that will combine index guiding in one direction with photonic band gap in other direction. So examples are shown here. So let us assume a two dimensional dielectric waveguide. The permittivity is this one, epsilon equals 12. So it's a 2D material into the plane, as you can see. So we are only bothered about x and y dimension. So the height or the width of this material is 0.4 a. What is a? A is basically the period. Okay. So this is a slab, and this is, or you can say this is a continuous waveguide, and this is a periodic dielectric waveguide, right. So in the periodic dielectric waveguide, we have used dielectric squares. The dimension of the squares are given here, 0.4 a times 0.4 a, and the period is, lattice period is a. Okay. So in both cases, there is a conserved wave vector k that you can see along x direction, okay, because of the translational symmetry, and that results in guided modes. So if you look into the band diagram of the waveguides, okay, for TM polarized modes, okay, that will be like kz equals 0. So they are basically in plane. So you are able to see that for the continuous one, you do not actually have a band gap. Okay, you have a even band one here and then odd band one. Okay, and this is the light cone. Okay, and in the case of the periodic structure, you are able to see that even band 1 and even band 2. Okay, we will come to this discussion later, what is even band and odd band and this light cone. I am just trying to show you that with this kind of periodic structure, you are able to get a band gap. Okay, and so the left one, as I mentioned, it's a uniform waveguide, and the right one is a periodic waveguide including twice the irreducible Brillouin zone. So you could have actually done up to here, but just to show it, you have taken twice the irreducible Brillouin zone to show the entire curve, and you are able to see a band gap in this case. So as I mentioned, the blue shaded region in these graphs are basically the light cone. So they are basically nothing but the extended states propagating in air. Okay, these are not the guided modes. Okay. However, in this region you will have guided modes. They are labeled as even or odd depending on the y equals 0 mirror symmetry plane. So if you take, this is y equals 0 is this particular plane. So along this plane, if it is symmetric, you call it even. If it is asymmetric, you call it odd. Okay, and the waveguide is symmetric under reflection, because if you cut it at the middle, or if you put a plane at the middle, you will see top and bottom are equal. So you can say that the waveguide is symmetric upon reflection. So consequently, all the guided modes can be classified as either even or odd depending on the mirror reflection in this particular plane. And one can see that in this case we have only one even band and one odd band, and even band is having the lower frequency, so it is the fundamental mode. Okay, so it has got the fewest nodes, that is why it is fundamental, and it is also having the lowest frequency. Now if you look into the field patterns, let us look into the field pattern and understand what is even and odd. So at k equals pi by a, that is the Brillouin zone edge, if you take the Ez electric field distribution and if you try to see along y equals 0 plane, you will see top and bottom part are actually equal. So this you can call as even bend 1. In this case also, if you take a y equals 0 plane and compare the top and bottom, you will see they are symmetric. So that is also even. So you can call it as even bend 2. Why this is bend 1, this is bend 2, this has got 1, 2, 3, 4 nodes. This has got 1, 2, 3, 4, 5 nodes and so on. So it has got more number of nodes and lowest energy. So this is the lower fundamental mode. Okay. How about odd mode? You can see if you take a y equals 0 line here, you will see that this part and this part are basically inverse. So one is positive, one is negative and so on. The red one shows positive, blue one shows negative. So they are basically antisymmetric. So you can call this as odd mode. Okay. Now, okay, this we have already discussed. Now let us look into the band diagram for the waveguide. Okay. So in case you take a 3-dimensional strip, it means it has got a finite width and thickness. So width is also finite, thickness is also finite. So this actually becomes a 3-dimensional dielectric strip. So it is basically suspended in air, and then the holes are having a periodicity of A, and these holes are cylindrical holes. So if you try to plot the irreducible Brillouin zone, okay, so you are actually plotting half of it. If you want to get this entire thing like this, in the previous case you can plot up to double of the irreducible Brillouin zone, that's up to you. But here also you can see that in the case of odd modes you are able to get a band gap. Okay. So here the odd modes are shown. Okay. So this is basically EO1 mode and EO2 mode. Okay. So the plot is of Hz. Okay. So let us look into the band diagram, and here we can identify M and E modes. Now what are M and E modes? This is basically E mode or the TM mode, and so these are basically E bands, or you can say fundamental E bands, or you can say TM bands, and M bands are basically the TE bands. They are shown in red and blue. Okay. And this is the light cone. Okay. And you can see these are the different modes which are possible. This is very much similar to the band diagram that you have seen in the previous lecture, just that only difference here being that we are seeing it for a particular finite structure like a 3-dimensional dielectric step, and we are strip, and we are only calculating the half the Brillouin zone. So these are the two odd modes and even modes. Okay, sorry, odd mode 1, odd mode 2, as we can see, and this shows you the distribution. So here you can see that in the first case the modes are concentrated in the dielectric the air holes, whereas in the second case the modes are basically concentrated in the dielectric strip around the cylindrical holes. Okay. Now if you want to introduce a point defect in this dielectric periodic dielectric waveguide, what you can do? You can actually make one of this hole a defective one. Means you can actually change the dimension of one particular hole, so that the spacing between one pair of holes can be increased. Okay, from say A to 1.4 A. So that way also you are actually introducing defect. So what happens, this is from the top, you can see that this is how the the magnetic field pattern will look like, and this is from the side. Okay, so here you will see that the holes are actually the magnetic field is actually getting decayed from the center. So there is a kind of confinement in the cavity. Okay. So, there are resonant modes possible in that particular point defect. This is also shown from the top. Okay. So, the strong localization, as you can see here as well, okay, or you can see in these two cases. Okay. The dielectric structure is shown in this yellow pattern that you have already seen. The field decays only inversely with the distance in the lateral dimension. So, the field decay is shown here. You can also see it this way, that the field strength is decaying, and this is because of the slow radiative leakage. Okay. And that is true, because there is a defect after that, the field is getting confined, but outside that it will be decay. So, with that we understood that we are able to make periodic dielectric waveguides of different shapes to confine or to engineer the band gap and get some properties out of it. So, one example from the Bragg grating, if we go back, so it is basically this particular Bragg grating you are making in the fiber. So, we are calling it as fiber Bragg grating. So, you take a standard glass fiber, okay, which is basically guiding light by index guiding. You just that you have to modify the index of the core in a particular pattern, that high low high low high low and so on. So, you are able to create a kind of Bragg grating on the fiber itself. So, in that case what will happen, one particular wavelength will get reflected, or a band can get reflected, remaining will get transferred. So, if you take this kind of input signal, red to blue, all the colors are there, but say you have designed this Bragg grating that is resonating at the reflection is maximum at say green. So, the green will be stopped and all other things will be passed other than green. So, this way you can use it for filtering purpose. Now, let us look into the another type of application of photonic crystals, which are photonic crystal slabs. Now, these are simple structures with only one dimensional periodicity that can be used to confine light in 3 dimension by combination of band gap and index guiding. So, remember that photonic crystal slabs or planar photonic crystals with 2 dimensional periodicity, but a finite thickness. Okay. Now, because they have finite thickness, they are not exactly 2 dimensional photonic crystals. In 2 dimensional photonic crystal, we assume that to have they can be very infinitely tall. Okay. But here, despite there is resemblance with the 2D photonic crystal, the finite thickness in the vertical direction, they introduce some qualitatively new behavior, and because of which they are slightly different from the 2 dimensional photonic crystals. Just as the periodic dielectric waveguide differed from photonic crystals in 1 dimension. So, if you look into the band structure or band diagram of a 1D photonic crystal and a periodic dielectric waveguide, though they are more or less similar in nature, but there is certain difference. Here also you will find that because of this finite height or thickness, this photonic crystal slabs. So, this is basically a slab of the dielectric materials. Okay. So, you have low index material, then high index material, and then low index material. Here also you have something like that, but it is an inverse one than this structure. So, these 2 structures are basically complementary. This is a array of rods, this is an array of holes. So, right now you might understand that why we need rod slab and hole slab. One will give you band gap in one particular mode, the other will give you in the other mode. So, these are the examples of photonic crystal slabs. They basically combine the 2 dimensional periodicity, that is in xy plane, and they have index waveguiding along the z direction. Okay. So, if you take rod slab, that is basically a square lattice of dielectric rods in air, and you can consider hole slab, these are basically triangular or hexagonal lattice of air holes. So, ideally you should say cylindrical air holes in dielectric slab. So these are the dimensions we have taken. So the rods are having radius of 0.2 a. A is standard, A is the lattice constant, right? Here everything is in terms of lattice constant, so they can be normalized to any other. They are normalized. So if you whatever value you pick as your lattice constant, you can find the corresponding radius. And the slab has been taken to have thickness of 2a. Okay. So this is the thickness for this one rod slab. If you take the whole slab, the radius of the holes are 0.3a and the thickness of the slab is 0.6a. Okay. So these are the dimensions you have taken, and then when you calculate the photonic band diagram for this rod slab and hole slab, you will see the following. The rod slab favors a TM like gap and the hole slab favors a TE like gap, something very similar to what you have seen in the previous lecture for 2D photonic crystal of dielectric rods and hole array, right. So the band diagram for photonic crystal slabs, these are suspended in air. So again the blue lines are basically the air cones. That means these are basically all of the extended modes which are basically propagating in air. Okay. And below this, whatever you see here is the guided mode in by this slab. Now if you see the blue and red bands, they indicate, the blue indicates TM, red indicates TE like modes. Okay. And this is the brilliant zone. So we have actually gone through the brilliant zone. This is the square one. So you have the important points of gamma, X, M and gamma. This is a triangular array or hexagonal array. So the brilliant zone is a hexagonal shape, but the irreducible brilliant zone is again a triangular shape, as we have seen in the previous lecture. So you can take gamma, M, K and gamma. These are the points you go through. So you can see that there is a clear TM like gap and this is a TE like gap. Okay. So we are saying like here because they are similar to the ones we have seen for the 2D photonic crystals, but these are slabs, the finite thickness ones. Okay. Now in this particular slab array, let us try to introduce some defects that we have discussed in the previous lecture. First thing, let us introduce a linear defect in the slab. So you can actually, in 2 or 3 dimensional photonic crystals, you can form a waveguide by removing one row of the rods. That is possible. And how it is done? In this case, the row is removed gradually. And to show how exactly how the defect is forming, okay, you can actually see that the radius on the top is getting shrink. Okay. So here you have all the rods are having identical radius, but towards the top they are getting all tapered. Fine. So these are the two views of reduced radius waveguide fabricated in a rod slab. Okay. And this is designed to operate in near infrared wavelengths. So what are the material? So the material is gallium arsenide for the rods, and those are having low index aluminum oxide as the pedestals. Okay, stands. So this is the top view of that particular array. It's hard to see from the top view because you are actually from the top you will not be able to see the conical shape, right. So how does it help? Here you can see that if you have reduced radius rods, say the rod's radius has been changed to this one. So for a defect of rod radius of r equals 0.14 a, and at a particular wave vector k x a by 2 pi is given as this. So if you take this particular value and if you simulate the results, you will see that you are able to waveguide light along this particular defect. And here also you can see the confinement along this particular line defect or reduced radius rod. So the electric field is mostly confined in this region. Okay. You can also have photonic crystal slabs without by removing, or you can actually take a whole slab and remove a particular row of holes. That can be also another defect. So here you can see such an example. So this is a beautiful slab of holes, and this particular line of holes have been removed. So this is basically this one, and this is the SEM, scanning electron microscope image of this particular missing row of holes. So how it helps? Again, this will help you to find out some particular modes can be guided through this, and these modes need to be in the, why we do the band diagram, because these modes should be in the gap bands. Gap band means the frequency of those modes should lie in the band gap of the crystal, so that they are not able to leak out into the crystal. If they are within the allowed bands, what will happen? You excite or launch a particular mode, they will be able to leak into this particular slab. So that is not good. You want to actually guide it. So they should not leak into any of these cases. So the frequency should be chosen from this particular gap band, and that is why calculation of this photonic band structure for any of these particular slabs is also very important. The next important topic is photonic crystal fiber. Now why it is important? Because you understand the importance of optical fibers, that is the backbone of this telecommunication, internet and everything, right? So you actually require optical fiber from astrophysics to medicine, everywhere. So a traditional fiber has got a central core which has got a cladding of slightly lower refractive index, right? And the light is basically guided through index guiding. So the light travels through the higher refractive index material surrounded by a region of lower refractive index material. So this is a typical photonic crystal fiber. So what happens here, in the cladding region you are basically incorporating a periodic structure or a photonic crystal, and that photonic crystal should be having band gap of the wavelength that is being carried in the core. So how it will help? It's a simple explanation that light from the core should not be allowed to leak into the cladding. So if that particular wavelength falls within the band gap of that photonic crystal that has been made in the cladding, so there is no way out, so light will be guided through the core endlessly, right? So photonic crystal fibers, they are also called microstructured optical fiber. They can be divided into a few broad classes, okay, according to whether they use index guiding methods or band gap methods for optical confinement. So there are different ways of working. So let's see what is that. So first one is photonic band gap fibers confine light using a band gap rather than index guiding, okay. And band gap attractive is, a band gap confinement is very attractive because it allows light to be guided within a hollow core. So the attenuation will be not there, okay. So in a silica core fiber, when light travels, there is the attenuation, but if light is able to travel in a hollow core fiber, that is the core is made of air, okay, in that case there is very low attenuation. So as I mentioned, this minimizes the effect of loss, undesired nonlinearity and other unwanted effect which comes from the bulk material, like silicon induced effect in fiber that can be removed if you use a hollow core fiber, okay. Now there are three types of photonic crystal fiber. So one can be a Bragg fiber, that is one dimensionally periodic cladding of concentric layer. So you can actually design the cladding using a Bragg grating, okay. These are called as Bragg fibers. Then you have seen this one, hollow core fiber by a band gap. So here it is actually doing a band gap kind of guiding, because you have a hollow core and you have a photonic crystal around it. So whatever is being guided cannot escape into this periodic photonic crystal. So this is band gap kind of, or you can say this is band gap method or band gap confinement. And the third one is holy fiber, where you have a solid core that supports light propagation through index guiding, but the cladding is now made of photonic crystal again. So in this two case, this is the difference. This is a holy core, okay, and this one, the core is solid, but it is called a holy fiber, okay, because the cladding is basically made of holes, because when you actually have holes around, that will effectively lower the refractive index, and this is how you get a high and low refractive index material in the fiber, okay. So this is how the fibers are drawn. So photonic crystal fibers, they have enormous practical advantage over the periodic structures that we have discussed. First, these fibers can be created through a drawing process, fiber drawing method. So what you do in this case, a scale model of the fiber or preform is created, which is typically centimeters in size. So you actually make the actual shape of the fiber like this, and then you heat the preform and pull it. So it is like bubble gum being stretched, and you can draw the micrometer thin fibers, okay. So in this way, hundreds of meters or even kilometers of fiber can be drawn from a single preform, and as you are drawing, you can actually make a roll or coil out of it, okay. So here is some band gap calculation of the index guiding fiber or the holy fiber, as you can see, okay. So the easiest photonic crystal fiber to understand are those that employ index guiding. As you see here, they guide light by the virtue of smaller average refractive index of the cladding relative to the core. So by introducing these air holes, you have brought down the refractive index of the surrounding medium. So that works as the cladding, and the light is basically guided in the core. So here we have taken like triangular array of air holes. So this is the core. The core can be thought of as a missing hole in the center. And how does it help? One might hope that it would be sufficient to consider only the average index contrast between the core and the cladding in this case, but in fact you have to understand the band diagram to find out that which all modes are basically guided in such a particular fiber. So that way calculating the photonic band structure for this one is also very important. We will not go into that much details because it is not that advanced course. I am just showing you the possibilities. So here are two possibilities of the fundamental mode that can be generated in such a fiber. As you can see, one can have this kind of electric field orientation, the other one can have the orthogonal one. So these are basically doubly degenerate fundamental mode. So their polarizations can be nearly orthogonal. In one case it is Ex, another case it is Ey, okay. Now in an ordinary index guided fiber, one can go up to higher and higher frequencies, okay, or smaller wavelengths, and more guided modes can be pulled below the light line, right. So higher order modes are also possible, but in that case, if you see here in the solid core holy fiber, okay, when you reduce the wavelength or increase the frequency, okay, so the effective index basically touches that of the silicon, okay. So they can actually remain endlessly single mode, okay, regardless of the wavelength. So that is something very interesting, that in this particular case you can have single mode throughout. So the question will come, why are the higher order modes absent? That you can see from here, the reason is that the effective index contrast between the core and the cladding in the holy fiber keeps on decreasing at smaller wavelength, okay, rather than remaining fixed if it was a effect like homogeneous cladding. So in this case, the confinement for higher energy modes become very weak, because the delta n between core and cladding is very less. So those higher order modes leaks out, so they will not be guided. Okay. So the higher order guided modes, they remain below the light line, so they are basically air, so they will be leaked. So in the limit of small lambda, in this particular limit you can see the effective indices of both the modes and the light line, they approach the index of 1.5, which is of the bulk silica, right. So that is how you can say that in this kind of solid core holy fiber, higher order modes cannot be sustained, so only single mode can propagate. So that is also very good, there is no multi-mode interference and all these things. So there is a huge promise of photonic crystal fibers in the future. So here are some electron microscope image showing you how exactly the hollow core fibers look like. So this is hollow core fiber, okay, and this is a omnidirectional mirror. This is again hollow core, okay, omnidirectional, because in all the direction you have a mirror kind of thing based on Bragg, okay, Bragg cross section. So you have alternating layers of high low dielectric and so on. So this is one particular fiber, and this is another fiber, you have silica glass and air, okay. So these are the air holes, okay, these are the zoomed one, you can see this is electron microscope image of hollow core holy fiber, okay. So this part remains as it is, so there is no hole, air hole is missing here, okay. So this is the holy fiber section, right. So this way you can understand that there are so much of applications of photonic crystals, 1D and 2D photonic crystals, and even 3D are also being used as cavity. So by introducing point defect, they are very good resonators. We will not go into all those applications here, but in short these are the more popular usage of 1D and 2D photonic crystals, and with that we will stop our discussion here. So in the next lecture we will go into the basics of metal optics or plasmonics, and this will be the final thing. This lecture concludes the discussion on photonic crystals. If you have any questions on photonic crystal, feel free to email me at this particular email address mentioning MOOC on the subject line. Thank you.